Hi everyone, thanks for joining us and welcome to the first ever littleBits Google On Air Hangout. My name is Erin Mulcahy. I'm the Community and Program Manager here at littleBits, and I will be monitoring today's Q&A. We're very excited to be hanging out with our friends from NASA Goddard who are here to share their experience and expertise as well. As you may know, littleBits makes an open source library of modular electronics that snap together magnets for prototyping, learning, and fun. This past April, we launched the Space Kit, which was developed in collaboration with NASA. The kit takes on one of the most universal and intriguing fields of all time, space, and demystifies it for everyone to understand, learn, and most importantly, participate. We've received a lot of great feedback and questions on this collaboration and wanted to give our amazing community the chance to ask us questions on just about anything. So today on our panel, from the littleBits team, we have Aya Badir, who is the founder and CEO, Crystal Prasad, product designer, Rory Nugent, electronics engineer, and on NASA's side, we have Ginger Butcher, who is the education and public outreach lead for NASA's Aurora mission, as well as Matt Volkar, an optics engineer at NASA Goddard. And just a reminder to our viewers that you can send the panelists your burning questions through the right side of the Hangout window, or tweet us at littleBits with hashtag #AskLittleBits, all one word. So before we get started, let's just take a minute to get reacquainted with the Space Kit and watch the official video.
T minus 8, 7, 6, 5, 4, 3, 2, 1, 0, ignition. Liftoff. At a velocity of 17,545 miles an hour.
Yeah, that was great. Let's do another one. This time I want you to really wave.
Okay, so hopefully you were able to see the video. Let's dive into some questions. The first one, sending over to you, Ginger and Matt. This one's from Dennis in South Carolina. How did the partnership with littleBits come about? Do you normally work with startup companies?
I will take that one. NASA works with lots of partnerships, and this particular partnership came about when I was looking at some of the activities that I'm doing out with the public, with students, trying to teach them about the electromagnetic spectrum, coming up with the actual circuits to do remote, like transmitting sound via light. And it required a lot of pieces and alligator clips and other types of electronics that often broke, particularly if you're working with a lot of people, a lot of kids, and maybe a large event. So when I saw the TED Talk by Aya, and I saw this unique way of putting together the modules with magnets, and they could, you know, come apart and go back together pretty easily, I thought this might be a perfect way to do some of the activities we're now doing at NASA. And we went ahead and put together a proposal to one of our research grants here at NASA to come up with a way that we could combine the activities that we're doing and do them with these littleBits to try to make it easier, simpler, and possibly even more obtainable for lots of other people to do. And then we approached Matt about the possibility of using these bits to develop a spectrometer, which we're still in the process of working on, but we came out with a lot of really interesting activities as part of that experiment. So we won the research grant, we put together a Space Act agreement, and that's how this particular project got started.
Awesome. I would love to hear your thoughts on the partnership and what it meant for littleBits to work with such an amazing organization like NASA.
Erin, can you say that again? We missed the last piece of your question.
Hi, Aya. Just wondering if you could speak on your thoughts on the partnership and what it meant to work with such an amazing organization like NASA on the project.
So I grew up in Beirut. I didn't grow up in the US, and even from Beirut, we used to watch the NASA launches that were happening when I was growing up, and it always felt like such a far dream to be able to work with such a huge organization that has affected humanity in such a big way. And so when I first received the email from Ginger in 2012, it was an incredible feeling to have piqued the interest of NASA and hearing somebody say that we could maybe help them further their mission even further. So it was very, very exciting. Initially, Ginger was thinking about maybe we could give them a discount on some of the modules or maybe just give them instruction on how to do some experiments. But I felt like there was a bigger opportunity to learn a bit more about some of the experiments they wanted to communicate, and for us to make a kit that is focused solely on communicating those experiments. I think some of the younger generation doesn't always know what's happening inside NASA. They don't understand how it relates to them. Even some of the older generation, we don't always, it's not front of mind. And so with this kit, what we want to do is take some of the anecdotes, some of the inside stories, and some of the mind-blowing scientific experiments and really be very true to them and be very scientific, but at the same time showcase them to the outside world in a way that is accessible and not intimidating.
And a follow-up question on that, Amanda from Plymouth, Massachusetts is wondering, when you start developing a new bit or a kit at littleBits, what's the development process look like? How do you actually go about making a new bit?
So I'm going to pass that question on to Rory to speak on behalf of our electrical engineering team.
Sure. So at littleBits, we're actually a team of 7 engineers now. I started over a year ago, and at that point we had 3 engineers, so we've over doubled at this point. It's pretty exciting. Every bit that we make tends to start with an idea, and sometimes those ideas come from Aya. They come from Paul, our director of R&D. Sometimes they come from feedback from the engineering team or the design team here. And sort of how we prototype them is kind of up to us a little bit. It depends on the bit we're working on. I have a couple bits here that I can share and talk about. I'll start with, this bit is a little sentimental to me because it's the first bit I worked on while I was here at littleBits. This is the redesign of the bar graph. So sometimes we prototype them like this. We put them on proto board. That's one way of doing it. This is what the bar graph actually looks like, that you're probably most familiar with. You can see, I'll just demo it really quickly. Let's see. Got the remote trigger. So what I have here is a circuit with the old bar graph, the redesigned bar graph, and we have a remote trigger on here, which is what's used actually in the space kit. So that's the remote trigger. I have an IR remote in front of me, and you can see every time I press a button on the remote trigger turns the bar graph on. So this is one way of prototyping it. We put it on proto board like this. Sometimes we do crazy things like this. This is actually a remote trigger that was built by our lead engineer, Jeff Littman. He doesn't like breadboarding. he likes doing things like this. So this is another example. We have the speaker, which is also in the space kit, and this is we breadboarded this time instead of protoboarding it, so that's why it looks a little bit different here. Sometimes breadboarding can be a little unreliable, so we like to actually solder things here. Some other examples are, they look crazy, but this is an example of the wireless receiver. So you're probably most familiar with them because they look like this. This is the pair, the wireless transmitter and receiver pair. And this is the receiver. So in this case, we soldered it to protoboard, but then because we had a microcontroller on the wireless transmitter receiver, we decided to go with an Arduino for our prototype. And then lastly, this is just another example of a soldered prototype board. This is our light sensor. So I guess I'll do one last little demo. This is the light sensor. This is an old bar graph. And I'll use a light from my phone just to kind of show you.
This is live before littleBits.
There we go. So that's the redesign of the bar graph and our early prototype of it. So this stuff takes a while to build. And you can see it's pretty unwieldy, so when we actually come up with the final product, it is way nicer, and that's why we sell it that way. That's about it. Anybody else?
Awesome.
So just a note on that, partially the reason we go through what we're doing is we try to make the modules still retain the complexity and sophistication that the circuit has, but make them simpler for people that are not necessarily engineers to use. And so it's a very fine balance between making barrier to entry really low, but keeping the ceiling of complexity, I think, that you could do really high, because the goal is to not dumb anything down. On the contrary, the goal is to empower you to create highly complex, highly programmable, wireless communication devices and projects and experiments that you otherwise wouldn't have been able to do while starting with one brick at a time.
Thanks, Aya. Matt, would be curious to hear, as an engineer at NASA, how is the development process similar or different from what the team's doing at littleBits?
That's a good question. It's actually pretty similar. We don't necessarily do the breadboarding, but what we do is sort of larger scale. So in general, when we're defining a mission, for example, or an instrument, we'll have some, we'll basically get a bunch of engineers from different disciplines together, thermal, mechanical, electrical, optical, the whole, every discipline we need, put them all in a room together, and then start brainstorming what the various requirements are. And the important thing is that everything that we do has to trace back to what the science wants. So the scientists will come to us and say, we want to make a certain particular measurement, and we need to measure this quantity with this accuracy. And that sort of drives the engineer's design process. Then we can go ahead and figure out what the instrument will need to look like, what kind of capabilities it'll need to have. And then we do, depending on how advanced that design might be, we'll either start with some models in a computer, which is very similar to some of the breadboard designs that you just saw, where it's kind of ugly and a mess, but it's just kind of get an idea of where all the connections occur and what the interfaces are. And then from there, we'll refine it into something that's a final package like the littleBits, but ours will be an instrument on a satellite or a spacecraft or something like that. But it's a very similar sort of process of starting from scratch, getting an idea of what it might look like, putting together the interfaces, and then refining it from there until it meets the requirements that we need it to meet.
Thanks, Matt. And yeah, I mean, one of the goals of littleBits is to really simplify the prototyping process. And this year, littleBits has released a lot of powerful modules. Crystal, I know you work a lot on the product development side and projects. Are there any you can show us over there, kind of show us what's possible using modules and some other materials?
Yeah, definitely. I'll show some. We have a few projects that we wanted to show off of what you can do with the space kit. see, Rory, I might need your help for this demo. So one of the projects that we worked really closely with Ginger and Matt on was actually developing a project called data communication, where we're using the littleBits to simulate how digital signals work. So I can show you. So what we have here is 2 circuits on mounting boards, one with a light sensor and a speaker, and then the other one that Rory has with a microphone connected to a phone plus an IR LED. So we'll do a demo really quick to show how you can actually play music wirelessly. I'm going to pull up a song. So what I'm doing, I'm actually going to tilt this a little bit so we can see the table. So what I'm doing right now is I'm just lining up the IR LED with the light sensor here. Let's see if we can get it on this one. Good choice. Yeah, Beatles, classic. Oh, so I actually just cut this signal. I'll end it after this. So what's so great about this project, I'm just going to go down again, is that what we're actually doing is music from the phone is going into the microphone bit right here, and it's being decoded into light pulses by the IR LED, and then the light is traveling right through air and then being received by this light sensor right here, and then being converted back to sound waves through the speaker. So it's a really amazing way. It's a really amazing way to show how NASA is able to use longer wavelengths like that. Not necessarily IR, but I think they use more like radio waves and stuff like that. But to showcase how digital signals are run and how we are able to communicate with things that are very far away and in outer space. So this is just one activity that we tried to simplify. It's a very complex idea, kind of like what I was saying earlier. Demystifying these really complicated ideas that NASA does experiments with every day and making it accessible for people to recreate.
Awesome.
Ginger, actually, the funny anecdote. Sorry, Erin. The funny anecdote about that is this project came out of the anecdote that that NASA uses sends music wirelessly to the astronauts to wake them up
on the ISS. Yeah.
So you can create your own little wake-up signals.
Love that. I wonder what music channel they choose. Ginger, this one is a good question for you. Angel Mills on Twitter wants to know, what will students learn from the littleBits space kit? I know a lot of the reason why NASA was involved was for the educational support for a lot of the activities you were already doing. So I would love to hear the background on that and how you're using them currently.
Sure. So essentially what we wanted to do was have kids have a hand-on experience with the electromagnetic spectrum. We interact with it every day. They may not realize that, whether it's the IR remote control for your TV, using your microwave, or even a wireless controller for your video game. All of these are waves in the electromagnetic spectrum, and so is visible light. And everything that we do at NASA basically comes back to the electromagnetic spectrum. The instruments that Matt talked about are basically measuring some aspect of the electromagnetic spectrum. So one of the activities we've done is we've put together a energy sensor. Essentially, it's the same light sensor that you saw demoed earlier, but this one is actually hooked up to a number bit, which is also what came with the space kit. The number bit was essential bit, and they didn't have this when we first started talking with the littleBits, but we needed some way to quantify the data, some way to quantify the amount of light, because that's what we do. We measure, we want numbers, we want to be able to do the science. So when we actually did this activity with the kids at the Science and Engineering Festival down here in DC, as well as Earth Day, and they were able to assemble this circuit, the light sensor circuit, and they got to experiment with trying to make the number change by covering up the sensor and getting a lower number. And essentially, this is what our instruments are doing. They're flying above the Earth, they're looking down, and they're trying to measure how much of a specific wavelength that the sensor's measuring and get some measurement of that. So for example, we took that and we made this experiment called Measuring the Atmosphere. Now this one is in the space kit along with the energy sensing circuit activity. But the idea here was the water in these bottles represent the air in the atmosphere. And this is a clear bottle if the atmosphere was completely clear or empty, but obviously there's stuff in it. There's oxygen we breathe, there's ozone that protects us that's in the atmosphere. So we've added a little bit of milk to these two bottles to represent the particles and molecules in the atmosphere. So we tell talk to the kids and explain that as the light from the sun, and we have a bright LED on the top, travels through the atmosphere to the surface of the Earth, the light is interacting with the atmosphere and doing different things, different properties. So we're going to take some measurements and find out what's happening. So essentially, and I'll kind of do this in a real quick method, but we have, if you can see, this first bottle, if you measure how much light is actually getting all the way down to the bottom, it should go almost all the way to the top, I think like 99. All the light's going through to the surface of the Earth. And this is good if you wanted to take a picture of the surface of the Earth and have a nice clear Google image, if everyone's used Google Maps, which uses some of our NASA imagery. But as you add more stuff or particles or molecules in the atmosphere, something happens. We get less. I think that's less. I can look at it this way. Yeah. Well, we have a lot of light in this room, so we get a little bit less. And then when we add even more, and there's particles also from like volcanic eruptions, and we have like sand, aerosols, all kinds of stuff in the atmosphere. So essentially, more in the atmosphere, the less is getting to the surface. And if you are a scientist that wants to study the surface of the Earth, and we have a lot of folks, the Landsat mission and Terra and Aqua mission, but there's also scientists that want to study what's in the atmosphere. How much ozone, protective ozone, is in atmosphere? Where is the most pollution located? So what they actually do, it's a different kind of measurement. Imagine if this is sensors on the satellite and it's looking down through the atmosphere. Okay, so we get a lower reading with the clear bottle because most of the energy is going in a straight line, straight down to the surface. And then as we add more to the atmosphere, more light. Well, we usually ask them what's going on with the light, what's happening to the light as it's traveling down. Why are we getting more light showing up as we have more stuff in the atmosphere? And as you can almost see, there's this kind of a glow. And what's happening here is the light is scattering. And what we do when we're looking at atmospheric chemistry, like at the ARA mission, we weren't measuring the amount of light being scattered. This is similar to, think about why the sky is blue, that classic question. Particles can scatter light like the milk in this bottle, but also, or particles of milk, but also molecules. So the nitrogen and oxygen in the atmosphere actually scatters the blue wavelengths of light, and that gets scattered all over the sky, and that's why the sky is blue. So essentially, this cool little activity that we were able to do, and actually teaching kids how, basically you're building a sensor or an instrument similar to what we would put on a satellite. And this one's just measuring visible light, but there's other instruments that measure UV or IR light. And you can learn how we're basically measuring the scattering of that light, and that's how we study our atmosphere.
I love that you can do that, Ginger, with just some materials like you have hanging around the house, just a few bottles, milk, water. Yeah. It's amazing. You can just recreate those. And if anyone at home is interested, we have all the projects and lessons on our littleBits project page. And like I said, just grab a few things hanging around, and you too can start doing some really cool experiments. We do have a question coming in from Be More Carl. This one we can queue up for the littleBits team. What tricks can you do with the light sensor? Does it detect IR? They say, I think my droid uses IR. Rory, can you speak to that one?
I mean, as you can see from the example that Crystal showed before. We were sending infrared light with the IR LED. Was here, and this puts out infrared light, and we were using the light sensor over here to receive that infrared light, so the light sensor does pick up infrared light. You can't see the light coming out of the infrared light because it's actually somewhat invisible to the human eye. There is some infrared light that's called near infrared, which you can see, and things like your phone might pick it up if it doesn't have an IR filter on it. Sometimes sort of consumer cameras and things like that. The iPhone, for example, actually filters out infrared. So if you're trying to use the camera on your iPhone to see if this is working, you actually won't even see anything. But I know some Android phones will show you the infrared light because they don't have it.
But if you're looking for tips on how to use the light sensor with the IR, we actually have a really great blog post online. That's the tips or tricks for the IR LED. I think it's littleBits.cc/tips. But what our design team did is actually found some IR filter, I think from old floppy disks. I don't know if you knew that they did that. So you can actually put that over the light sensor if you only want to capture IR and not get too much noise from other light happening. So there's a lot of interesting ways to use the light sensor with the IR by using materials like that.
You can also go to like camera stores, and they will sell IR filters. And in the past, I have done little minor experiments with theatrical gels where you try to filter out most of visible light while still letting through a little bit of infrared.
Awesome.
So before we move on to more questions, I just wanted to show a couple more projects so people can see what they can make. This is a really fun project that you can go off on. It's a satellite, and I think so. Crystal will tell us more about that. And then the other project that we'll show is this makeshift Mars rover. So let's show them to you really quickly, and then we'll keep taking questions.
Yeah, so this is actually more, sorry, I'm just covering Aya's face completely on the satellite. This is actually a great example of how to use the light sensor. This is another project that I worked really closely with Ginger on. And the idea here is to teach people how to recreate your own satellite dish. I mean, it's an object that we see every day, either driving down the street or walking down the street. So I think it's important to demystify it in that way, and it's great that we can use littleBits to do that. So the idea here is that you can actually build your own parabolic reflector and simulate how a satellite dish captures data and information. So what we did is we used the light sensor and put it at the focal point of the satellite dish so that when light from the atmosphere beams into the dish, it'll bounce, if it's perfectly parabolic, bounce directly into this focal point, which we put our light sensor, and then it'll actually put a reading out of the number bit right here. So you'll see it's actually pretty sunny. The number bit is almost at 99. But I think it's an interesting way to use the light sensor to actually capture and record environmental data like that. And all the instructions of how to make this is in either online where the space kit is, or also in the booklet that comes with the space kit. And then the next one, now we can see Aya again. The next one that I pointed out is actually using littleBits to create a makeshift wireless rover. So this is one that we made. I'll tilt this a little bit so that you guys can see it. So here we have two circuits. One is actually using our new wireless bits here with some dimmers of how to control it. I'll turn them on. And then basically what's happening is if I move, I can use a dimmer to actually move the claw on it. And I can make it dry. So this is sort of an analogy to how you could start to create remotely controlled vehicles like the Mars rover. I can capture something.
Battery's dying.
I think my battery's dying. There we go. If I see a form of life, I can grab it, I guess. Yeah, this is another example of a project that you can learn how to make online. And then we also, you can see us, we also have instructions of how to make a wirelessly controlled Mars rover using the remote trigger that Rory was talking about earlier.
Hey, Crystal, Jason Sanchez is wondering, is it possible to 3D print extra attachments?
It is. That's a great question. So right now we don't actually sell these extra attachments, but all of the files get uploaded online to the project page. So if you happen to have a 3D printer, or if you are familiar with like Shapeways, or part of a hackerspace, you can definitely download the file and print it yourself. Or if you wanted to create your own accessory for a project, we love seeing what people come up with. So you can upload those files to the project page.
We also have an exciting competition coming up in the next coming weeks. I can't say too much about it, but it will answer your question very well. So stay updated. Stay up to date.
NASA, back to you. I have a question from the Twitterverse here. Is the NASA satellite, is the Aurora the only NASA satellite that features Earth's atmosphere?
No, that's actually it's the Aura satellite, which is Latin for breathe, and it was the actually started out as the one of the Earth Observation System missions, EOS, and Terra was the first mission for land. Then we had Aqua, then we had Aura, and even though they look at the land or the water, there's other instruments like Ceres and so forth that can look at the temperature in the atmosphere, clouds, aerosols. MODIS and Moppet on Terra do a real good job at looking at aerosols. So all of these instruments have to look through the atmosphere to the surface of the Earth, and in some way, as that process happens, they're looking at parts of the atmosphere, such as aerosols. We even have active remote sensing satellites that use radar or lasers, and lasers will actually shoot down. They can measure the elevation of the surface of the Earth, or the ice. We actually have one that looks at the thickness of the ice sheets in Antarctica and Greenland and the poles. And in the process of that laser going through the atmosphere and back up to the instrument, it's interacting again, scattering, absorbing, and we're actually looking, we can see how that light is scattered to tell things like the location of volcanic ash, the distribution of volcanic ash and other particles in the atmosphere, and that's called LIDAR, when you're actually using a laser to look at the atmosphere.
Thank you,
Back
Ginger.
to you.
Aya, this is a good one for you and potentially Crystal. Space is an amazing theme for Kit. How do you actually go about deciding how the kits are themed, and do you have any potential hints for what's coming down the pipeline?
So, I mean, the first thing I'd say, it's important to know that littleBits is a library. So we now have over 54 modules, lights and sounds and sensors, ranging from the very simple, like an LED, to the very complex, like wireless transmission. And really the goal of littleBits is to keep growing this library so that every single combination works. And we already have billions of different combinations of circuits that you can make. And the reason we make kits is basically to get you started, so that you have something out of the box that you can get started with, get familiar with littleBits, and sort of learn about this larger library that is for prototyping, for learning, and for fun. So we started, the first few kits that we had, the base, premium, and deluxe, were focused on general electronics. We wanted to break down the concept of electronics and make it accessible to everyone. And then we started to take on one field at a time, where technology is very prevalent, where there is a very engaged and passionate community, but there's also a lot of misunderstanding of that technology. And we took that field and broke it down and made it accessible to people to reinvent. So the first one we did that with was the synth kit, which we launched last November. That took on music synthesis and music in general, and allowed you to create your own analog synthesizer. And then the second one that we themed was the space kit that we worked on with NASA to take on the field of space and break it down and make it accessible. And I'm not going to say what's coming next, but it's a really, really, really good theme that people are really going to be excited about. But the key thing is that no matter where you start, it doesn't matter. Any kit that you start with is just an entry point. All the bits and all the kits work together in whatever configuration you want. So it's really just whatever tickles your fancy.
So Andrew in New York wants to know, are the bits going to space? I guess that's up for either. So
I'll kick that one over to Aya's team.
Oh. So we have actually, there's a few different activities, 3 different initiatives happening. We have Steve Heck, one of our educator ambassadors, has been working on getting littleBits tested for 6G. We have also some community members that we met that work in JPL that want to try to get them into space. And so there are different activities happening. So there's nothing definitive yet, but we definitely want to see them up.
Ginger and Matt, if you had a wish list for a bit that didn't make the kit, what would you like to see added to the collection?
Well, since Matt is still struggling with this spectrometer, I'm going to turn over to his work that he's been doing with the spectrometer.
Well, so related to the spectrometer, I think we have all the bits we need, but one that would be really cool to have and to play with, and I think would be a lot of fun for the transmission type experiments that are included in this kit, would be a laser bit. But I don't know if we can get that, because lasers are cool, come on.
And you might want to say something about the spectrometer that you were, like, well, the spectrometer is kind of how we break apart the bands of the electromagnetic spectrum so we can measure, get those specific measurements, right?
Right, so Ginger was talking earlier about using the instruments on the satellite to make measurements of individual wavelengths. And so when we look at things, our eyes see all the wavelengths combined together, and so what we need is an instrument to spread those wavelengths out so we can measure each one separately. And we use the spectrometer for that. So I think one of the experiments in the kit is using a CD to create a diffraction grating and to create the spectrum. What that does is it actually spreads the light out into the red, green, blue, yellow, all the colors you can see. And so we were working on a spectrometer that has a diffraction grating in there that's basically like the CD that takes incoming light and spreads it out, and then we would move, using the littleBits motor and the sensor, we would move the sensor through the wavelengths of light, and in each position measure how bright that particular wavelength is. So you could point it at a red object, for example, and you would see a brighter peak in the red portion than anywhere else, and then you could point it at a blue object and see a brighter peak in the blue. And this mimics exactly how our actual spectrometers on orbit work. They spread the light out, we measure each individual wavelength and determine relatively how bright one is compared to the other, which gives us information about what we're looking at. So we're still working on that. There's a few bugs we're trying to work out.
It's okay, maybe in the future. This one, Matt and potentially Rory, this one's coming from user Jack and Jude. She's wondering, does using the satellite to receive an infrared music transmission increase the distance you can transmit?
Are you on this?
I can take a first crack at it. So does using infrared increase the distance we can transmit? I think I understood the question correctly.
Yeah.
Yes and no. So there's a couple different pieces that go into how well you and how far you can transmit something, but ultimately really what it comes down to is how strong your signal is, how powerful it is. And so the stronger the signal, typically the further you can send it. Now, the few exceptions to that is that what is between where you're sending from and where you're receiving it to. So, for example, let's say, for example, we had a satellite much further away than it could ever be, and we were on the other side of a nebula, which is a cloud of dust. In that case, infrared would help a lot because infrared light passes through that dust much better than shorter wavelength of visible light like what we saw, what we can see. Ginger mentioned earlier about why the sky is blue. And the idea is that longer wavelengths penetrate dust or particles much better than shorter wavelengths. Redder colors penetrate better than bluer colors. So in that sense, yes, infrared would work better. But really, as a first answer, is basically how strong is the signal to begin with.
And the inverse square law of light, right?
Oh, I wasn't going to go into that.
Oh, okay. Well, there is an activity that you can download from littleBits about the inverse square law of light, which essentially is the further you get away from your light source, the less amount of light is actually getting to your object. Now, the laser, basically that's all the light waves in phase, right?
And all in one direction.
All in one direction, so it's concentrated, so you're going to get a much further distance. Like we have lasers that shoot down from the satellites through the atmosphere to the surface of the Earth and bounce back, and they can measure that. So you could certainly go across the room or much further if you're using a laser as opposed to any of the LEDs.
Great. littleBits, this question is for you. Could you add filters to the basic light sensing project to simulate taking spectrometer readings?
Yeah, I think you can. I'll just say briefly. We did something, I know some of the littleBits team got to go visit NASA and look at the spectrometer that they were working on, which was really exciting to see it in action. But one activity that we did include with this space kit that's like a really simple way that NASA was discussing earlier is actually using a CD as diffraction grading with like one of our bright LEDs, and you can actually start to see basically a rainbow that you would get to see the spectrum of light happening. I think it's a good question for NASA to see how well their spectrometer is working right now. Did you want to add something?
No.
Yeah. So yeah, I would turn it over to them.
Back to you, Ginger.
Okay, I'll give a basic intro and then I'll send it on to Matt. One of the things that that he can probably explain, there's really two ways that you can measure a specific part of the spectrum specifically, and use a diffraction grading, what we're talking about, splitting that band apart and then measuring each part, or you can filter it. You can put a filter in front and you know that you're only going to get that green light or that red light coming through. But we found out that the filter didn't work too well, as the previous question was, is the sensor sensitive to infrared light? Well, all of the filters we used would filter out all the other colors, but not the infrared, and it would require a little more fancier filter, more expensive, so we didn't go that route, and we went back to actually dividing the light apart and using the servo. And Matt, did you want to add anything to that?
I mean, that pretty much covers it, but yeah, I mean, there's lots of different places to get filters to play with the light. I mean, even I think you can buy colored saran wrap, and that would do the same thing. Just very simply, cover up the light and let only those wavelengths through. The trick is that even though some of the filters you might buy, as Ginger just alluded to, maybe they look red or green or look blue, they actually let through a lot more colors that we can't see just because they're still mixed together. So it may look like a green filter, but there's still some red light getting through and still some blue light getting through, just not as much. And so if you try to play around with that with the light sensor, you might trick yourself into thinking, well, it's a blue filter, but I see red light, and that may not make sense because the red light is still actually getting through, just not very much of it. That was something we ran into in the lab that confused us for a while.
Awesome. Thank you, Matt. We have a question from Joe. So on the littleBits team, we always see the community make amazing projects using the space kit, but also the other modules as well. And Joe wants to know, what's the biggest single surprise that you've seen from a littleBits user? And I think this is referring to things that they've made. Aya, do you want to take that?
I mean,
there's new ones every week.
Yeah, every week there's new ones. Actually, it's hard to say. The one that I've been most excited about showing up lately is a series of instruments that one of our community members called HTDK. I think it is his username. Basically, he makes these large mechanical and robotic train tracks that have littleBits sensors embedded in them. And then he connects them with synth bits so that they can become instruments. So basically, you have these large robotic, sometimes made out of Lego, sometimes made out of other material tracks, where as you're touching and activating littleBits bend sensors or others, it's starting to play music. And so he's done them with music that he's created. He's done them with Mary Had a Little Lamb. He's done them with 2 interacting instruments, and they're really incredible.
Yeah, I think one of the coolest projects I saw recently was the line-following robot that came across our desk. They made it with, I think, 2 LEDs, 2 light sensors, and then just simply logic bits. This was even before the Arduino was ever released too. That was a really fun project.
What's yours? What's my favorite? I'm trying to think of a recent one. I know there was one. Did you guys see the one recently that was made by Cord?
Oh, the character.
Yeah, recently Cord, our partner in the last kit, made this like animatronic puppet that would like use bits to like move its mouth and make sounds at the same time. It was a good balance, I think, of like humor, but it was very sophisticated at the same time. So I found that.
Ginger, do you have a favorite project?
Of my own, maybe?
Well, we've seen a lot of great projects from you, but if you've seen any that really were amazing.
I was just trolling through the projects page, and I'm trying to think of. There were some pretty cool things, but I saw, I like the ones that are super simple, and so that's why I like the pizza box phonograph. So that's basically a motor and power and paper cone and a needle and a pizza box to play a record. So that's kind of, I like to be able to keep them as simple as possible and using household stuff that you can get a hold of readily.
And Ginger, you made that before the synth kit came out, so you must have good premonition to the littleBits. Great. Well, actually, we are probably going to wrap unless Ginger, Matt, do you have any closing comments or questions you'd like to pose to the audience that they can take with them and try to tackle with their littleBits kit?
I do have a challenge. With the bits in the space kit, and something that I've just thought of, and it doesn't really relate to what we do at NASA, but it does kind of relate to waves. Using that parabolic shape and that classic, the idea of a satellite dish that's actually taking in electromagnetic energy and using the light sensor, that is in the kit. But there's a microphone in the kit as well. And if any of you have seen a football game, or they're on the sidelines and they've got those big like salad bowl parabolic, basically it's a microphone, parabolic microphone. So challenge you out of household stuff, I don't know, salad bowls, umbrellas, to make a parabolic microphone. You can use the microphone bit, you could probably plug in some headphones, and you'd probably be able to like listen to your neighbors.
I mean, one thing I would say is I'm really excited to see how, there's more people uploading projects every day that they make with this space kit, but I'm also excited to see what the team at NASA does, because I would love to see what happens with the spectrometer and like other experiments that they can actually use the bits in.
Awesome.
And I think in general it's kind of fun to just answer questions that people have. We recently put up a forum at discuss.littlebits.cc where we've been able to start interfacing with our users a little bit more. In the engineering team, we're a little bit insulated from the people who buy the bits. So
we quarantine our engineers.
It's probably on purpose. But it actually would be fun on a regular basis to get questions and get to answer them from our users.
Absolutely. And if anyone is an educator, will also be at the ISTE's educational conference at the end of the month in Atlanta, and we'll be running a workshop with the Space Bits, so it'll be a great chance to try them out then. But in the meantime, thank you so much, everyone, for participating, for your questions, and we look forward to seeing what you make and for hopefully joining us in future Hangouts with littleBits and our good friends at NASA Goddard. So thank you, everyone. Have a great rest of your day, and we'll talk to you soon.